Okay, hello everybody. We've done an updated version of this video due to some changes on the relationship sheet. So, at National 5 you were possibly taught that a geostationary satellite orbits the Earth above the equator and appears to stay in the same spot above the Earth. This is because it orbits the Earth in a period of 24 hours, which is the same time as it takes the Earth to rotate once on its own axis. And you may also have been told that the height of a geostationary satellite above the surface of the Earth is 36,000 kilometres. So the question is, why 36,000 kilometres? Well, let's see if we can use our working centripetal force to answer that question. So firstly, period of a geostationary satellite is 24 hours. The radius of the Earth, 6.4 times 10 to the 6, and the height above the Earth's surface of a geostationary satellite is 36,000 kilometres. That's 3.6 times 10 to the 7 metres. Now if we add those two distances together, we'll get the total radius at which the geostationary satellite is orbiting, and that's 4.24 times 10 to the 7 metres. Now, what is it that's actually keeping the satellite in orbit? Well, it's the gravitational force of attraction. And from your higher work, you should remember the relationship F equals gmm over r squared, where, in this case, big M is the mass of the Earth, small m is the mass of the satellite, and r is the distance between the two of them, or the radius of the orbit of the geostationary satellite, and F is the gravitational force of attraction that is providing the centripetal force to keep the satellite moving in a circle. So let's equate these two relationships for the gravitational force of attraction and the centripetal force. Remember, big M is the mass of the Earth and small m is the mass of the satellite, which appears on both sides, so we can cancel it out from both sides and cancel out one of the r's on the bottom on each side, and that leaves us with gm over r equals v squared. Now v is the tangential speed of the satellite in its orbit around the Earth. R is the radius of the orbit measured from the centre of the Earth. M is the mass of the Earth, and of course big G is Newton's universal gravitational constant. Now, the speed of the satellite can also be given by the relationship speed equals distance over time, and it travels a distance of one circumference of the circle in a time equal to the period of its orbit. So that's 2 pi r for the circumference over t for the period. Now, if we square that whole thing there, we'll get an expression for v squared. So it'll be 4 times pi squared times r squared over t squared. And then we can substitute that into the relationship just above it and then do a little bit of mathematical jiggery pokery. Let's rewrite it then. So gm over r is going to be equal to 4 pi squared r squared over t squared. And we want t squared to be the subject of the relationship here. So if we do a little bit of cross multiplication here, so let's move the t squared over to the left. Let's take the r up from the left hand side, so it becomes 4 pi squared r cubed all over, and bring the gm down. Okay, and so we've now got an equation that gives us the relationship between the period of a satellite's orbit and the radius of its orbit. Now, for a geostationary orbit, remember, for a geostationary satellite, it has to have a period equal to the period of the Earth. That's 24 hours. And if we work out 24 hours in seconds, that's 86,400 seconds. We can substitute that into the relationship, along with the value for big G, that's Newton's universal gravitational constant of 6.67 times 10 to the minus 11, and the mass of the Earth, which is 6 times 10 to the 24 kilograms. I better put my units in for big G as well. It's Newton metre squared per kilogram squared. Okay, let's do that. Let's substitute all them in. The period was 86,400, so let's square that. That's equal to 4 times pi squared over 6.67 times 10 to the minus 11 times the mass of the Earth, 6 times 10 to the 24. Let's bracket all of that, and that's times r cubed. So we can rearrange this for r cubed then and find the radius. So r cubed, if you do all that on your calculator, gives you a value of 7.57 times 10 to 22. Now that's r cubed, so let's cube root it. And we get a radius of 4.23 times 10 to the 7 metres. Now remember, that's the radius of the orbit measured from the centre of the Earth. So if we want the height of the orbit above sea level, then all we have to do then is subtract the radius of the Earth from that value. So 4.23 times 10 to the 7 minus the radius of the Earth, 6.4 times 10 to the 6, gives us an answer of 3.6 times 10 to the 7 metres. And that is 36,000 kilometres. So the height of a geostationary orbit above the surface of the Earth is 36,000 kilometres. Now, in previous advanced higher papers, candidates were asked to derive that relationship, but it now appears on your relationship sheet in this form, with the gravitational force equated to the centripetal force in its 3 different forms. So all you really have to do now is rearrange it to get it into the form more commonly known as Kepler's Third Law. Now Kepler, that's him there, Johannes Kepler, he was around before Newton. But through direct observation and using other people's data, he theorised that the period of a planet's orbit around the Sun squared is directly proportional to its mean radius cubed. And it was only much later that that theory was found to be correct by the discovery of Newton's universal gravitational constant, which in itself wasn't discovered until after Newton had died. But we now know it's got a value of 6.67 times 10 to the minus 11 Newton metre squared per kilogram squared. And the m in this relationship is the central mass that's producing the gravitational field around which some other body is orbiting. And in the case of our geostationary satellite, that was the mass of the Earth. Now that begs the question, how was the mass of the Earth determined? And the radius of the Earth? And how was big G determined? Well, for that we need to go back and talk about some of the godfathers of astrophysics. We need to go way back to this guy, Aristotle, one of the earliest scientists. He believed that the Earth was the centre of the solar system and that everything revolved around the Earth. And that idea remained for a long, long time. In fact, the Greeks knew that the Earth was a sphere. In fact, Eratosthenes, this fellow here, was the first guy to do an experiment that not only proved it was a sphere, but they worked out the radius of the Earth. What he did was he let some sunlight shine directly down at a well, and at the same time measured the shadow that was cast from a tower that was about 800 miles away. And then using some geometry, was able to work out the angle between the two and hence the radius and curvature of the Earth. And he got a pretty good result 2,000 years ago. He was actually only 1% out from the accepted value today of 6.4 times 10 to the 6. Now we have to go forward about 2,000 years, because remember at this time it was thought the Earth was the centre of the solar system. This fella here, Nicholas Copelicus, he was the first guy really to suggest that the Sun was the centre of the solar system. Copernicus's teachings went against the ideas of the Roman Catholic Church, and as a result he kept his ideas pretty much a secret, and he was very, very unpopular for a long, long time. But eventually his views became accepted, and we now have the heliocentric, the sun-centred model of the solar system. Galileo was an Italian who managed to get his hands on a telescope, and his discoveries and observations made huge advances in the late 1500s and early 1600s. Around about the same time, but working in Germany, was Johannes Kepler. Kepler didn't have a telescope, but what he did have was an awful lot of data, an awful lot of measurements that were made by this guy, Tycho Brahe. Now, Tycho Brahe is famous, more famous probably because he had a metal nose. He lost his nose in a sword fight with his pal. They were arguing over who was the best mathematician. So, Tycho Brahe. But he spent years and years measuring the distances to planets, especially Mars, and the period of orbit of Mars and the inner planets. Now, Kepler took Tycho Brahe's data and was messing about with it, drawing graphs and trying to find relationships, and he found an astonishing relationship between the period of orbit of a planet and its mean radius of orbit. And he laid down 3 laws about planets moving in orbits. Firstly, that planets don't all move in circles, they move in elliptical orbits. Secondly, when a planet is orbiting a star, it maps out equal areas in equal periods of time. And thirdly, and this is the one that we're dealing with just now, he discovered that the square of the planet's orbital time, the square of its period, is directly proportional to its mean radius cubed. Now remember, there was no mathematical derivation of this relationship. This was just arrived at by looking at the data, the actual measurements of the planets moving across the night sky without the aid of a telescope. An incredible discovery. But really, the next piece of the puzzle was provided by a man you've heard of. That was Isaac Newton. You've already met Newton's universal law of gravitation, F equals g/m over r squared. But what a lot of folks don't realise is that Newton died before the value for big G was found. We had to wait a long, long time after Newton's death until that was discovered. And indeed, that was discovered by an English scientist. He wasn't born until after Newton had died, but Henry Cavendish managed to do an experiment with 2 brass balls. He knew the mass of them, he knew the distance between them, and he was able to work out the force of attraction between them. He shone a beam of light onto a mirror that was attached to a rod, and by measuring how much the rod had twisted, he was able to measure the force of attraction between the brass balls, and hence big G was found. And that just leaves the mass of the Earth then. How was the mass of the Earth determined? Well, lots of people have tried to do that experimentally, but the value that we have today comes from Newton's universal law of gravitation, F equals g/m over r squared, and the weight of an object is equal to its mass times the gravitational field strength of the Earth. Small g we can measure directly by dropping objects and measuring the acceleration due to gravity, and we know the value of small g is equal to 9.8 metres per second squared, or 9.8 newtons per kilogram. So if we equate both of these relationships, mg equals g/m over r squared, we can cancel out the mass on either side, and that leaves us with g equals gm over r squared. We know that small g is 9.8 newtons per kilogram, or 9.8 metres per second squared. We know what the radius of the Earth is from Eratosthenes, 6.4 times 10 to the 6 metres. We know what big G is from the Cavendish experiment, 6.67 times 10 to the minus 11. And by rearranging that relationship and substituting all the values in, we can work out the mass of the Earth. It'll be small g times the radius of the Earth squared divided by big G, the gravitational constant. So subbing all them in, 9.8 times 6.4 times 10 to the 6 squared, all over 6.67 times 10 to the minus 11. That gives us an answer for the mass of the Earth of 6.0 times 10 to the 24 kilograms, and that's the value that's on your data sheet. Now, there's a slightly interesting wee aside to this story, and it revolves around a mountain in Scotland. That mountain's called Schiehallion. And before the mass of the Earth was discovered using Kepler's Third Law, then an early effort was made to measure the mass of the Earth. So what they needed was a perfectly shaped mountain. And if they could figure out what the mass of this mountain was, then by holding a pendulum beside it and measuring how much the pendulum was deflected, then they could measure the force of gravity between the two. If they knew the two masses and the distance between them, they could work out big G. Unfortunately, it wasn't that successful. So, hopefully that shows you that there's a lot of people involved in us getting to our current state of play in terms of our knowledge of the universe. That's it for this one. We shall see you in the next one.